What we're going to look at today is we're going to look at properties of relations. Specifically, we're going to be looking at reflexive, symmetric, and transitive relations. One of the things that's really important about these kinds of relations is that they're only going to be defined on what are called binary relations. So a relation is going to be binary if it's defined on A cross A. And what that means is that essentially our input and our output spaces are going to end up being the same. This means that it has a domain of A. So when we have our relation defined on A cross A, that means that our domain is called A. And the properties of these relations in this section are only defined for binary relations. So consequently, we don't utilize these definitions, symmetric, reflexive, and transitive, for anything other than binary relations. So let's look at the first kind of relation. These are called reflexive relations. And so by definition, a reflexive relation is if for every x in the domain of R, XRX is true. And what that means is that XX is in R. And graphically, that's going to mean that every x in the domain has what's called a self-loop. And we're going to look at those in just a moment. Let's suppose that A is Juan, Albert, Brian, and Rondale, and XRY means that X thinks that Y is a great person. So for our set, we first have that Juan thinks that Rondale is a great person. That's our first Cartesian pair. And then we have that Juan feels that Albert is a great person. We have Brian thinks that Rondale is a great person. Albert thinks that Brian's a great person. And now, because these people are actually great people, they think that they are themselves great people. And so Juan thinks that Juan's a great person. Rondale thinks that Rondale's a great person. Albert thinks that Albert's a great person. And Brian thinks that Brian's a great person. And what I just drew there are called self-loops. And so this self-loop, because there's a self-loop for every one of these vertices, what we have here is we have a reflexive relationship. On the one hand, we can see JJ, RR, AA, and BB is inside of the set R. And also that in the graph, we have a self-loop for every single one of the vertices. So hence, that means that this is reflexive. On the other hand, we have another idea that is called being anti-reflexive. And being anti-reflexive is not just simply being not reflexive. R is anti-reflexive if and only if for every x in the domain of R, XRX is false. And so what that means for us is that XX is never in R. Graphically, that means that no x in the domain has a self-loop. So let's take a look at an example. Let's suppose that A is Z plus and XRY is true if x divided by y doesn't equal 1. Well, for XRX to equal true, that means that x divided by x doesn't equal 1. But this is false. So what that tells me is actually that XRX ends up equaling false all the time. So it's never going to end up being true. So like, for example, if I had the node 1, we are never going to get a self-loop for 1 because 1 divided by 1 equals 1, and we need it to be not equal to 1 for our relation to be true. So we look at that definition, we can see that this is in fact an anti-reflexive relationship. Let's take a look at another example. Let's suppose that we have this group. We have Tony, Maria, Baby, Johnny, and Michael Jackson. And we have XRY if X is dancing with Y. Now what we know is that Johnny's going to dance with Baby, that Tony's going to dance with Maria, and in fact, Baby will dance with Johnny, and Maria will dance with Tony, and we know also that Michael's dancing with the man in the mirror. So he's got a self-loop on him. And so since he's got a self-loop, and the other nodes inside of this set don't actually have a self-loop, this is neither anti-reflexive nor reflexive. This is neither. So it's possible for us to have something be reflexive, have it be anti-reflexive, or have it be neither reflexive nor anti-reflexive. So to just review, a relation is going to be reflexive if XRX is true for every x in A. The relation is going to be anti-reflexive if XRX is false for all x in A. And it's also possible for a relation to be neither reflexive nor anti-reflexive. Let's take a look at another kind of relation. This other kind of relation is called a symmetric relation. So our definition for a symmetric relation is if A are B, if and only if B are A. So essentially, we can switch the order of A and B and we still get a true statement. This is essentially like having an if and only if we were thinking about these as conditional statements. So a relation R in A cross A is symmetric if for all A and B in A, if AB is an R, then BA is an R. Now that doesn't necessarily mean that AB is an R, but if it is, then that also means that BA has to be an R in order for our set to be symmetric. So graphically, if there's an arrow on the graph going from A to B, then there has to be an arrow going from B to A. So let's take a look at an example. Let's suppose that A is Juan, Albert, Brian, and Rondale, and XRY is defined as X shakes Y's hand. So let's say, for example, that Rondale shakes Albert's hand. We have that Brian shakes Juan's hand. And we have that Brian shakes Rondale's hand. Now notice there's not actually a line going from Albert to Juan. That's okay. But since we're shaking hands, if Brian shakes Rondale's hand, we assume that Rondale will shake it back. And if Rondale shakes Albert's hand, we assume that Albert will shake Rondale's hand. And if Brian shakes Juan's hand, then Juan's going to shake Brian's hand. If we set up our set R, it's going to look like this. It's going to have RA, AR, RB, BR, BJ, and JB to represent all of our different relations. What we want to notice is that if RA is in the set, AR is in the set. So what we have is we have that reflexive, that symmetric relationship there. We have RB and BR, we have BJ and JB, and since this is true for every single one of our pairs, that if I have a pair in the set, I'm going to have the other pair switched, this actually means that this set is symmetric. Now, just like with reflexive, we had an idea called anti-reflexive, we're going to have an idea called anti-symmetric. Now let's define something as anti-symmetric. Now, what it means for something to be anti-symmetric is it means, one, if for all x and y in A, if x doesn't equal y and xry is true, then yrx is going to be false. Essentially, that means that if we have an arrow from x to y, we will not have an arrow from y to x unless we have a self loop. So in terms of our directed edges, we're only going to have a directed edge that's going to go one way. So let's take a look at an example. Let's say, for example, we have a equals z plus, so only the positive integers. And we're going to say that x over y, our relation is that x over y is greater than 1. So if x over y is greater than 1, what that means for us is that x has to be greater than y. Well, in that case, yrx is actually going to indicate that since y is less than x, then y over x is in fact going to be less than 1. So yrx is going to end up being false. So while x over y greater than 1 gives me xry equals true, yrx is going to end up giving me false, right? So what we have here is we have an anti-symmetric, or excuse me, yes, an anti-symmetric relation. Let's take a look at another example. Let's say, for example, we have a equals z and xry if x over y is an integer. Now in this case, if x equals y, then x over y equals 1, and that's an integer. That belongs to z. On the other hand, if x doesn't equal y, then what we know, and xry ends up equaling true, then that means that x is divisible by y, or y divides x. And also, in fact, that the absolute value of y has to be less than x. If you kind of think about it, that's the only way that this is going to work, otherwise you're going to have a fraction. So what that means is that when I take y divided by x, this is not an integer. For example, if we had, I don't know, 6 divided by 2, we let x equal 6, y equal 2, 6 over 2 equals 3, but if I take 2 over 6, that ends up equaling 1/3, excuse me, 2 over 6, that equals 1/3, and that is not an integer. So here's another example, and in this case, the example fits in terms of if x equals y, we're fine, and so x equals y, true, and xry equals true, but yrx equals false. And so hence, once again, we are anti-symmetric here. What about the question, can a relation be symmetric and anti-symmetric at the same time? And so it seems a little strange that we'd have something be something and anti at the same time, but it turns out that the logic allows this to be true. If we look at our definitions, we have that something's symmetric if for all x and y, if xry is true, then yrx is true. And also anti-symmetric if for all x and y, if x doesn't equal y and xry is true, then yrx is false. Now, the thing here is that if xry is false, then both statements, the conditionals, will end up being true because their hypotheses are false. Okay? So what we have here is that if xry always equals false, then a conditional, this, say for example, this is our P logic, our P implies Q ends up always equaling true because whenever P is false, okay, P implies Q equals true. It doesn't actually even matter what our Q is. It doesn't matter whether or not yrx is false or yrx is true. What we have is we have both something that matches the definition of symmetric and it matches the definition of anti-symmetric. So you can kind of see things work a little bit strange when we're talking about relations when we have something that, you know, maybe has x or y always being false. So let's kind of review the idea of symmetry and anti-symmetry. One, a relation is symmetric if for all x and y in the domain, if x or y is true, then y or x is also going to be true. A relation is going to be anti-symmetric if for all x and y in the domain, if x doesn't equal y, and x or y is true, then y or x is false. So, on the one hand, for the symmetric, when we're thinking about what its graph looks like, every edge has the reverse edge, the edge going the other way. When it's anti-symmetric, we have the exact opposite. Whenever we have an edge, we're not going to have the edge going the other direction, okay, unless what we have is a self-loop. And it turns out that we can have a relation that can be neither symmetric nor anti-symmetric, and we can have a relation that can be both symmetric and anti-symmetric if x or y is never true for every element in the domain. The final relation that we're going to look at inside of this video is called transitive relations. A transitive relation is transitive if for x, y, and z in A, if x are y and y are z, then x are z. And so this kind of goes along with what it means to be transitive in a lot of mathematics. Graphically, that means if we have an arrow from x to y and y to z, then we can bypass y completely and go to z if r is transitive. So to be transitive, we have to have that relationship. Let's take a look at an example. Let's suppose that we have A as Adonassia, Bao, Kayla, and Dante. And we have x or y is true if x is heavier than y. So let's say, for example, that we know that Bao is heavier than Dante. We have Dante is heavier than Kayla. And we have Kayla is heavier than Adonassia. By the relationship of being heavier, what we know is that if Bao is heavier than Dante and Dante is heavier than Kayla, then Bao has to be heavier than Kayla as well. So we have to add in that part. We have to have B to C. In addition, since Bao is now heavier than Kayla, Bao is also going to be heavier than Adonassia. And we also know that if Dante is heavier than Kayla and Kayla is heavier than Adonassia, then Dante has to be heavier than Adonassia. And that just makes sense because that's the kind of relation that we're looking at here. So in this case, this relation ends up being transitive. So we can see we have B to D and D to C, so that means I have to have B to C. I have D to C and C to A, so that means that I have D to A. And since I have B to D and B to C, that means that, or excuse me, I have B to C and C to A, that means that I have B to A. And so that gives me all of my transitive relationships. It's really handy to know that something's transitive because it actually allows us to kind of bypass different elements inside of the relation. Let's take a look at another relation, see if we can see something that's transitive. Let's say, for example, Adonassia, Bao, Kayla, and Dante are our group again, and we have x r y if x shakes y's hand. Now, we have Adonassia shakes Bao's hand, Bao will shake Adonasia's hand, Kayla will shake Dante's hand, and Dante will shake Bao's hand. Now, the truth is we could probably assume that Bao will shake Dante's hand back, and Dante will shake Kayla's hand. But notice I've got A to B, and now notice a couple of things. One thing to notice here is that I have A to B and B to A, but I don't have a self loop A to A. Now, if I were to have that self loop, A to B and B to A, or excuse me, if this was a transitive relationship, A to B, B to A, and we'd have to have A to A because that's the transitive relationship right there. If I had C to D and D to B, I'd have to have a C to B because I'd have to have that transitive relationship. So in this case, I have no A to A or no B to B, C to B. So this is not transitive. Now, technically, there is such a thing as being anti-transitive. However, we're not covering it in this section. It's not actually utilized all that much. So in this case, we'll just say that it's not transitive rather than saying that this relationship is in fact anti-transitive. Let's review the properties. Reflexive, symmetric, and transitive properties are defined for binary relations. That means that both X and Y are going to belong to the domain A. A relation could be reflexive or anti-reflexive or neither, but it can't be both. A relation can be symmetric, anti-symmetric, or neither, and it can be both if X or Y is never true. And a relation is either transitive or it is not. I hope you enjoyed the work that we did here on the properties of relations. Understanding the properties of relations can be really handy and crucial for understanding relations at a deeper level. They allow us to categorize relations in different ways, and you'll see that they're going to show up a lot when we talk about graphing and also about matrices. If you did like the video, go ahead and click on like. If you have any comments or you want to ask me a question, go ahead and put them in the comments or questions. And if you like the work that I'm doing, go ahead and subscribe to the channel. You'll see a lot more math like this.